Swayam Prabha. Digital India. Educated India.
Hello and welcome to the Microsystems Fabrication Laboratory. I am Shantanu Bhattacharya, and I'll be teaching today, I'll be demonstrating some experiments on photolithography, which is a very essential component of MEMS, for MEMS fabrication essentially. So let's go step by step in this. The first thing I would like to enhance and like to emphasize in such a laboratory is that you have to be really maintaining the cleanliness, and there is a certain attire which is useful for processing, and basically one needs to cover almost entire portion of the body and take the proper safety measures so that the particular operator in question who is doing the experiment is not affected, and also the experiment is done in a dust free environment. So let's look at the components one by one. This right here is one of the fundamental components used in such a laboratory. It is known as the fume hood. Essentially it provides a class 1000 clean space or clean area which is just underneath or behind this particular panel. There is essentially a blower unit which circulates and causes a laminar flow of air inside this particular hood, so that typically all the dust which is around passes through a set of HEPA filters and the air is recirculated back, and there is absolutely no entry of dust particles from outside into the clean space. Most of the dust particles exit because of this continuous laminar flow operation. So other components, important components of the fume hood is basically an air track, a compressed air track which is kept for the purpose of cleaning wafers. Once we process these wafers, there is essentially a water connection which is used for again washing samples as you do the processing. And the very important component which is useful, or which is the primary component where all the processing is done, is actually a silicon wafer. So the silicon wafer is commercially manufactured by only a few manufacturers all around the world, one of them being MEMC, which is located in St. Louis. And essentially the wafer manufacturers have standardized processes wherein they produce different diameter wafers, including a 3 inches wafer, a 4 inches, 6 inches, so on and so forth. Now this right here is such a package or a box which comes from a wafer manufacturer, and it houses about 30 to 40 wafers in one of such packages. Let me give you a closer look as to how the wafers really look like. The wafers are all stacked in, as you can see here, in this particular fashion, and this again is packed in a super clean environment so that there is absolutely no dust on the wafer surface. So what we do right here is first take out a single piece silicon wafer, and I would like to illustrate how that wafer really looks like. So if you look at such a wafer, so as you see here in this particular fume hood, we have several components which we have kept inside. Normally, in order to maintain the cleanliness of the process, we use these aluminum foils, which you can see here is the silver foil, which is actually a clean surface and it is reusable. So it's actually a one-time use and throw basis. I can actually cut several pieces and cover this area and keep it as a base, and all the processes typically would happen on the top of such a foil. These components, as you are seeing here, some of the glassware which is around, or these tweezers which are meant for handling such wafers, have been already cleaned prior to this and heated in an oven so that you get rid of all the water around it. So they are actually adequate for handling these silicon wafers. So the first thing I am going to do is to actually unload a wafer from its box and make a separate container, or take a separate container or a wafer box and transfer this wafer. As you are seeing here, this right here really is a wafer box which is meant for containing a single wafer. For microfabrication, it is very important that, especially when the wafer is moving between workstations, we need to cover the wafer adequately so that we do not have any contamination as the workpiece is moving between stations. So in coating. Okay, so basically the first thing we have to do here is to transfer the wafer from this box into a separate carry box which is meant for holding just a single wafer. One of the reasons why we do that is that because we have to actually really protect the silicon wafer, especially when it is transferred between different workstations. So this is a carry box which is meant for that purpose, wherein there is a lid and then there is a small filter paper which is covered at the bottom, and this is used for handling wafer between workstations, particularly during the various process steps of photolithography. So we also use these aluminum foils to make super clean flooring while doing the processes. All the components like this glassware, as you are seeing, has to be thoroughly washed and cleaned and then dried in an oven so that there is no moisture, because essentially microfabrication is a lot about cleanliness. Okay? And so let's transfer the wafer from the box here. As you're seeing, this is the wafer box. This process only has to be done within a fume hood, because this prevents the chances of the wafer getting contaminated by the dust particles of the air. So we take a wafer out using a tweezer, as you can see here. Tweezer also is a very clean tweezer, and then essentially we use this box to load this wafer, and later on all the handling will be done using this particular box in the subsequent process steps, and then cover this with the lid. Okay. We close the silicon wafer box and keep it in a separate area. One of the reasons is that we have to be extremely careful while handling silicon wafers, because they are very fragile and essentially can crack even on little impact or stress. So we have to make sure that this wafer box is far away from the experimental setup, at least the main box is far away from the experimental setup. So the next step basically is the clean wafer. Although it is very, very clean, but we still need to do a surface treatment of the wafer so that number one, it can be made hydrophilic. Number two is that whatever organic contamination is there on the top of the silicon wafer gets removed. So one of the methods of doing that is by using an acidic solution called pirhana, which is essentially a mix of hydrogen H2SO4 or sulfuric acid and hydrogen peroxide. Essentially the pirhana is prepared by mixing 3 parts by volume of sulfuric acid with 1 part by volume of H2O2 or hydrogen peroxide. It's a highly exothermic process and results in a lot of heat release and fumes. And once the solution stabilizes a little bit after mixing, we typically use a glass rods to stir the solution and put the wafer on the solution and clean it for several minutes, about 6 to 7 minutes, so that everything which is organic on the top goes away. And then the idea is to kind of extract the wafer back and rinse it using DI water for a few times so that you can remove the acidic impurities, and then dehydrate it in an oven set at 95 to 100 degrees Celsius. So let us look at that process now. Pirhana is a very dangerous process, as I've already illustrated, and therefore you need to use a special protective covering. We are already wearing a safety glass as you have seen before. And now what I'm going to do is to wear a set of polypropylene gloves. These are acid resistant essentially and highly anti-corrosive, and it essentially prevents any kind of damage or contamination to the operator in case of spillovers. As you see here, you can just wear it over the secondary gloves that you are already wearing, and which is a clean gloves and for doing processing. Once this is one, we are almost ready for preparing the pirhana solution. So what we do is basically pour about, in this case about 90 ml of sulfuric acid, 98%. As you can see, this is a very, very dangerous chemical, and it has to be very carefully used. And then we'll mix about 30 ml of hydrogen peroxide. So what we do here is the following. We use all this pouring, etc., over this drain, so that in case there is a spillover, everything goes down the drain. Okay, so essentially opening this sulfuric acid bottle is also to be done very carefully. You use these gloves. So basically you open the acid bottle and keep the cap in safe place, safer area, and essentially now what you do is basically take this bottle and pour it in this beaker here very carefully and very slowly. As you're seeing here, pouring this is not a very easy job. Do it just about close to 100 ml. Okay, and essentially again keep this back in its place, cover this properly so that there is no chance of any spillover, and essentially close the lid. Okay, and we need to actually do a secondary measurement to ensure that the volume that you are using is proper. So use a measuring cylinder for that, and we need to pour exactly 90 ml here. So what we'll do is we'll transfer this sulfuric acid into this measuring cylinder and go all the way up to 90 ml. Which is just about complete now. So we take a new container in which we have to prepare the pirhana and slowly pour from the measuring cylinder the sulfuric acid. One thing we have to ensure is to identify the components which have already been used for containing sulfuric acid, because we have to wash them later on properly so that there is no risk of any experimentalist getting burned because of improper usage of that. Now we have to pour about 30 ml of hydrogen peroxide. So this right here is the container for H2O2, and the reaction is essentially an equilibrium reaction where there are a lot of hydrogen ions and hydroxides which are generated, and essentially it's an equilibrium process which coats a layer of hydroxide onto the silicon dioxide, the nascent oxide surface, and also creates a lot of heat. Okay, so basically we need 30 ml of hydrogen peroxide. So we open this and pour exactly 30 ml of hydrogen peroxide into the secondary container here. And keep it separately in this particular zone. Okay, we close this because it's a highly volatile material. It kind of evaporates, and so we need to ascertain that it comes back in its safe zone. So after we have independently poured these, we have to mix these two chemicals together in this beaker, and what I'm going to do is to now turn on the fume hood, essentially, because this is a very, very exothermic reaction, and essentially we have to also pull down the cover just about to a level where you can just put your hands inside and do the operations. So essentially now you'll be pouring the hydrogen peroxide into the sulfuric acid. This is a very critical part because this may actually explode. So as you see, when you pour the material, there is immediate reaction which takes place, and there is a lot of fumes which are generated, as you can see, and this fume has to be done in a very, very closed environment, and we have to wait for some time till this fume actually disintegrates or disappears totally, and pirhana is made in that process. So as you can see, the fumes are slowly settling down because essentially it is a very, very highly exothermic reaction. So what you do now is to actually use a glass rod and stir the solution very well so that the mixing between the hydrogen peroxide and sulfuric acid takes place. And then once this is ready, and mind you, this is a very hot chemical, and essentially you have to be careful while even pouring it into the separate petri dish, as I'll just illustrate in the next step. This is a glass rod. You cannot really use any other metal rod for doing this because the acid immediately produces the salts from the metal, and it also deposits the metal and takes it off, and in the process gets contaminated. So you have to always use a glass rod or a glass container for doing this pirhana making process. Once this is made, you rinse off the excess pirhana on the glass rod and keep this rod back into the container for H2O2, and this would later on be cleaned before we can reuse this again. And so what we now do is essentially take this pirhana, what we have prepared, and then pour it over our silicon wafer, which we will be keeping in this particular petri dish separately. Okay, so what we do is essentially we take our wafer, silicon wafer, and open this and clean. In order to clean this wafer, we put this wafer back over the petri dish here. As you can see here, we are putting the wafer in this petri dish, okay, and once we pour the pirhana, we can no longer use this metal tweezer for handling this wafer. So we'll have another separate Teflon tweezer for doing this wafer handling once it's out of the pirhana for washing and rinsing. Okay, so now we slowly pour this chemical, the pirhana, over this wafer, and it is extremely hot, as you can see, and essentially it also fumes as you pour it, and immediately, if you can see, there are the organic contaminations over the silicon surface has been immediately removed, and we store all this container later on for cleaning and using it, okay, for different applications. So now we keep this close and wait for about 10 to 15 minutes so that the wafer can totally get rinsed. So these, as you see, are now Teflon coated. These tweezers have tips which are coated with Teflon, or they can be complete Teflon tweezers which we can use. So what we are going to do is to provide a normal rinsing using distilled water, as you can see here, which is resting in the flask of this particular pirhana cleaned wafer sample, and then this would be followed by another wash of deionized water, so that it gives a super clean surface on the wafer. So what we do is we basically pull it out very carefully, because essentially this is all acid coated now and one has to be very careful, and then hold this over this edge and rinse it inside this with water, and rinse it on both sides. As you can see, all the water should typically go and rinse all the acid off the surface of the silicon wafer, and essentially once this is clean, in the next stage what we do is we take this DI water and slowly rinse it on the surface of this particular wafer. As you can see here, this is actually a squirt bottle which is squirting away the DI water on the top of the silicon wafer. So essentially, after completely rinsing it, you basically try to just change its holding location to a different area, so that you can rinse off the acid in the particular area where it was held before, and this way you can clean the whole sample. And essentially you can see now that the sample is more or less thoroughly cleaned, thoroughly washed, and it has a super clean nature on the surface. So once this is totally clean, we need to now use the compressed air to dry this particular wafer. But before doing that, we need to take care that the acid, etc., which is actually kept in open, needs to be kept away, so that there is no squirting of the acid in general. So now you take it. So this is basically an air nozzle. It actually sends in compressed air, and what we are going to do is to actually slowly use this nozzle to clean off the surface water, as you can see here, slowly from the surface. Okay, so essentially you have to move this thin film of water in the clean hood away from the side, so that you are actually left with a clean surface of the wafer, a clean shiny surface of the wafer, and there should not be any water drop in this manner on the surface. Typically all the water film should go away from the surface. Similar cleaning has to be done for the reverse side, and I am going to do that, as you see here, seeded from the compressed nozzle side towards the other side, and it is then rinsed off the surface by squirts of compressed air, as you can see. Okay, so this now really is a super clean surface for lithography to take place. So we put this sample, this clean sample, back into the wafer box, as you can see, and then we'll actually do a heat treatment of this particular wafer, so that it can get rid of all the water from the surface, and that way we have a completely dehydrated surface. We need to cover it at this stage, because the moment we move it out of this clean area, it can again become dusted and the contamination of the surface may happen. So this is how the Pirhana cleaning process of the wafer is done. So basically what we do now is to take this wafer that we just made super clean using Pirhana process and take it to an oven. The oven basically that we are using here is a gravity fed convection oven, which actually is based on the principle of free convection. There are a set of heater coils at the bottom, and there is a current of air, heated air, which actually makes the temperature uniform. There is a PID based controller using thermocouple, which is somewhere at the floor of this particular heater. This right here is that oven. So what I am going to do is to illustrate a little bit about this oven, and then basically use this oven to heat dry the wafer surface. So basically, if you look at this oven, really it is a shelved oven. As you can see, there is a fan which actually does forced convection along this whole area, and essentially the wafers are kept at various levels. The thermocouple is somewhere at the bottom. That is one disadvantage of this particular type of oven, because it sometimes is not a very good indicator of the temperature that happens. This right here is a controller. It's based on proportional integral differential controller. So as you see here, there are two different readings. There is a set point, and then there is a variable point where the temperature goes up and down based on what the set point is. In order to control this, basically, if you can see here, right here, there is a set option. So you press the set option and then take this up arrow or down arrow, and as you are seeing the figure here, which is the SV or the set value, is varying 89.3, 0.4, 0.5, 0.6, so on and so forth. So we take this all the way to about 100 degrees, which is important for proper hydration of the wafer surface, and once you reach 100, you basically leave the set key, and this is now set at 100 degrees. So this temperature, which is also the proportional integral differential temperature, is actually slowly equalizes this set value after a while, and basically there is some kind of a flickering around the set value. It does that flickering and slowly attains the set value point. So basically now, as you are seeing here, the variable value has almost reached 100 degrees, and this is time enough for our wafer to get loaded inside and get dehydrated. So what we basically do is essentially take the wafer box which we pulled out of the fume hood after the Pirhana clean, and then basically put an aluminum foil on the top of one of these shelves, and then slowly load our wafer sample so that we can get it heated and remove any water if present on the surface of this wafer. and the whole idea is to have a perfectly dehydrated surface of this particular wafer, so that it can be good for adhering to the photoresist that we essentially spin coat on the top of it before doing photolithography. So we keep the wafer in the oven for dehydration for about 10 to 15 minutes at about 99 to 100 degrees Celsius. The next step is to unload the wafer and start doing what we call spin coating of the photoresist. So what I am going to do is to just unload it and carry it back again. Please note that we are using the same wafer box for carrying the wafer, again from the for the constraint that it should not get contaminated while going between operating stations. So we slowly use the tweezer, which was again used for the other processes. This is again a clean tweezer, and we slowly pick up this wafer from the oven, transport it into the box here, and then convert this or cover this with the lid. So basically now we have a clean wafer which would take to the next station, which is actually the spin coater, where we will be doing the resist coating. So the next stage basically is spin coating the photoresist, and for spin coating the first thing that one needs to take care about is the grade of resist that one is using. There are many manufacturers of resists in the world. We will be doing negative tone photoresist here, which basically means that wherever light or UV light is used for exposure of the photoresist film, there would be a general cross bonding among the molecules, and the resist stays back, and the portions which are unexposed can be developed off. So really what you'd have is basically small features translated from the mask design onto the resist surface. And wherever light has fallen through the mask window onto the resist, the features remain. The other portions, the features go away after developing. So the first thing that is important here is to download the specifications of the particular grade of resist that you plan to use. And what we normally do is we use a resist from Microchem, which is actually a resist maker, and essentially we are using a grade of resist called 2025 SU8, which has a certain viscosity. And what the resist manufacturer really does, he really puts together an experimental curves for this particular viscosity. And so basically what he determines is what is the RPM at which we should spin the resist, so that a particular thickness can be achieved, and thickness defined by the RPM is really thickness of the feature that we are looking at. What it also does is it actually mentions about the temperature steps that you need to include in order to process the resist once it has been spin coated, and also after the exposure. It also mentions specifically about what is the exposure dosage which is needed, and what is the time for which the resist needs to be exposed, so that it can have enough cross linking and cross bonding. Just at the outset I said this process of photolithography is about developing cross bonds between different molecules, and that is essentially driven by reaction chemistry and has a certain rate. So it is very, very critical for us to be able to determine how much temperature is needed, what is the time point, or what is the time of holding for that particular temperature step. We also need to ascertain what would be a typical exposure dosage for all the molecules within that small window to get exposed, so that they get cross-linked very well. So essentially I would like to go ahead and make features which are about 20 to 25 microns thick. And for doing that, if you will see at this resist grade sheet, you basically get these curves here where it talks about what is the RPM on the x-axis here, and what is the corresponding film thickness that you will be getting. So when we are using a certain grade here, which is mentioned in this table here as you see, so SU8 2025, which is the lowest grade here, is really corresponding to a curve which is the least, this curve essentially here. And so corresponding to about 20 to 25 microns, what we find out is the RPM that we would need for this is about close to 3500 RPM. So I'm going to, in just about in a minute, set up the spin coater that we have here, and tell you more about how to program this machine, so that you can have the particular spin speed at a particular RPM and you can also be able to hold it at that spin speed for a certain amount of time. This right here is what we call the spin coder. Essentially, if you look into this machine closely, you have a spin stage which is represented here, which is here in this area. Essentially, the principle is you use vacuum for holding the wafer onto the spin table, and if you look closely into this particular area, you have these grooves here which are actually crisscross, and they are placed over the whole periphery of the spin stage. And the purpose of these grooves are that there is a vacuum track immediately below this, which is connected to a vacuum pump underneath this whole system, and essentially the vacuum propagates all the way up through this small center hole here, and then also propagates along these grooves and kind of holds together the wafer on the top of this surface. What is also important for me to tell you is that there is a control which is here, for which we can actually use for flexibly controlling the spin speed, also the amount of time for which we can hold at a certain speed, and also what is very critical for different grades of resist is the acceleration at which you can rotate in order to achieve a certain speed. So here in this particular example, what I will be demonstrating, as per the resist manufacturer specifications, the spin speed that we are using is about 3500 RPM, and also the spin speed has to be attained with an acceleration of about 300 RPM per second. Okay, and what it also mentions is that you have to hold at a certain spin speed for about close to 90 seconds for the spin coating to be uniform. I would also like to illustrate here that the resist, being a thick material, needs a little bit of time for uniform coverage over the whole surface. When we are talking about a circular wafer, what is very important for us to understand is that first of all, the resist that you are putting should be sufficiently covering the wafer, so that once the, so what is also very important for me to illustrate here is that really what we are doing is to spin the resist on the top of this circular wafer, which is about 4 inches or so, and we need to be able to ascertain. What is also very important for me here to illustrate is that the particular spinning operation should be able to adequately cover the whole wafer surface. This is a circular wafer of about 4 inches diameter, and the goal here is really that the resist should not have any gaps or any islands on the surface as you are spin coating it. So you have to ascertain how much area you need to initially pour or cover so that you have enough resist, so that essentially spinning process is nothing but centrifugation. There is a slow coverage of the surface of the resist which has been poured somewhere in the center by centrifugal forces. Okay, and so the whole idea is that you cover adequately and give adequate resist so that when it goes radially in all the directions, it should be able to have uniform coverage on the surface. So for doing this, what we would need to find out first is how to set up the controls in the particular spin coater and how to control the RPM time, the RPM per second rates, etc. So let's look at that in our next step. And corresponding to this program number, what all steps are there in the program are illustrated just in this particular region. So as you are seeing here in this, in the run mode, the step 1 of the program illustrates that there would be an RPM of 3500 RPM, which is attained at an acceleration of 300 RPM per second, and the time of hold for this is about 180 seconds, and this is with an option of vacuum operated, so that the wafer is pulled down while the spinning happens, and then finally you have to somehow change this program to suit to your requirements. So what we essentially do is to first use the program mode here, as you can see, to go to the number of the program. Suppose we want to make a new program here, so we find out we give a new number here. Let's say we want to make program 7, okay, and then we try to see or try to illustrate what is there in program 7. So we go to the mode option here. So basically what we now do is, after we have entered program number 7, we enter this program and then go to the mode option so that we can get a detail of what all steps are involved in this program. So here really the program is about step 1, and only it's a one step program, and followed by the end of the program, right? So it's one end. Now what we do is basically move to the next option here, and we get this RPM, which is actually 2000 in this particular case, as you can see. So what I'm going to do is to change this to 3500, which is our requirement, and we can actually hit enter here for the system to take this. And the time for which we need to hold this RPM is about 90 seconds. So we do 90 here and then enter the data, and the next step is what all revolutions per minute per second we need this speed to be. So we put the value for the acceleration 300 and essentially enter this value, and for our condition we need the vacuum to be on while the spinning is happening. So we just take whatever is the default, and that completes pretty much the program. Okay. So all we need to do is to now actually put the wafer back to the spinning stage, after which we will be doing the run operation. So what I am going to do now is to actually simply load the wafer onto the spin table, and then we have to also see whether the wafer is actually centered, which I will do a little bit later. And what I do is I just turn on the vacuum. You can see this light, the green light appearing here, which means that the wafer is now firmly held to the surface and it cannot come out, and it is basically clamped pretty firmly onto the spin table. Okay. So now it is almost ready to rotate and spin and essentially coat whatever is there on the surface of the material. So we would like to also have a look as whether this wafer has been centered, and the best way to do that is to close the lid and see from this transparent section on the top whether this wafer is really at the center of the spin table. In case it is not, then you can switch off the vacuum and again change the position in a manner so that the wafer can come pretty much at the center of the spin table. And the thing which we are ensuring here is that there should not be any wobble really of the wafer, and it should actually rotate at its own axis, and so it should rotate at its own axis, and that can ensure that there is no underutilization of the resist, which is at the very center of the particular wafer. So basically we have now placed the wafer, and essentially what we need to now do is just turn on the vacuum here. The light would come on, as you can see here. This is in the on mode. So basically the vacuum pulls the wafer so that it can sit onto the spin table, and then we have to also see whether the wafer is centered, and the way to do it is basically close the lid of the spin coder and turn this RPM on so that the system actually starts rotating, and see from this top transparent area where there is any wobbling in the particular wafer. Now as I can see here from the top, the wafer is more or less centered, and there is very less wobble. So I really did not do anything about position of the particular wafer. So I am going to switch this on. You see the wafer is moving inside, spinning, and essentially there is very less wobble, and we can do with it with this kind of a wobble. So I am going to now spin coat the photoresist on the top of this wafer by pouring the resist and then doing all this execution of the RPM cycle. And the moment the resist is spin coated, we also need to take this now for the twin step heating process, which I am going to describe in a little bit. So the resist, as I told you, needs to be heated, and one of the purposes why heating needs to be done is that there is a solvent which is really a carrier solvent for resist. It has really an epoxy resin which is dissolved in a carrier solvent, which is actually cyclopentanone, and essentially the purpose is really to transport the epoxy uniformly over the surface of the wafer in the spin coating process that we saw in the last step. And then we need to get rid of this solvent, because essentially that would ensure that the resist film is stable, it is hard enough, it is kind of equibonded, and before doing exposure it is very critical, because the mask would sit on the top of the resist. Okay? And so therefore if there is some undried portion or uncured portion, the resist is going to get damaged, and that is something that we do not want, because that would mean that the surface of the micro features that it would result in will also be damaged because of that process. So we need to ascertain that the resist is fully cured before taking it to the next exposure step. Now I would like to illustrate one fundamental factor here, is that we all know that because of heat addition there is a thermal expansion, and this is the thin film we are talking about. The resist is really a thin film, and so there may be due to rapid heating or rapid cooling, there may be a tendency of the resist film to warp over the surface and create undulations, and that is something that we want to avoid too, because we need to be as much planar as possible for the surface integrity or for the structure's integrity to be maintained. And so it's really a good idea to heat the resist in a stepped manner. Heat it at a lower temperature, maybe about 65 degrees or so, and then heat it to a higher temperature so that it is adjusted enough and there is no undulation or warping of the film as such. So therefore, we use hot plates for this purpose. Here, as you see in this particular illustration, there are two hot plates I have. They have been preset to the temperatures of 65 and 95 degrees Celsius, and each of these steps would have a certain time associated with it. So the spun coated resist on the wafer would basically brought in, and these plates would be used for heating these so that we can get a cured film of the resist on the surface. Basically close this and just start the spin coating process, and let the film that we have set kind of spread over the whole surface and create a thin film which is about 20 to 25 microns of this resist on the surface of the wafer. So now we have to be, now the resist is actually spun coated now, and we have to be very careful about removing the wafer. We have to hold it from a thin corner at the sides, because that is typically the area where there should not be any designs and structures. We'll just use a little bit of tweezer space for holding it and be extremely careful about handling, because mind you, at this stage the resist is actually a kind of liquid in nature. We have not cured, and before the curing the film is like tacky, and then if you have any stresses or any impact on the film, it's going to create a huge difference and make the film not behave properly. Also, we need to assert one basic fact, that the table that we are using for keeping or aligning our hot plate should be perfectly parallel to the ground, because otherwise there may be a possibility of the resist running to one side, thus creating a thicker film at one end, which is highly undesirable, because we want a uniformity in the film thickness, which also determines the sizes and nature of our structures and features. So essentially now the program has stopped, and I'm going to slowly pull, and as you can see here, there is a thin film of resist on the top of the surface. I'm going to actually take the wafer box here and then slowly use a small amount of space. So first thing we need to do is to close the vacuum so that we can decouple the wafer from the spin table. We take a very close, very small portion and bite along with this tweezer on that portion, and then slowly transfer the resist coated surface onto this wafer holding box. And then once we have done it, we actually cover it with this cover here, not press it very tightly, and then slowly move towards our next step, which is the hot plate, and keep it on the 65 degree set hot plate and wait there for about 3 minutes or so. So I'm going to put this wafer now on the top of this particular hot plate, which has been set at 65 degrees. So for doing that, we have to be again very careful about pulling this resist coated wafer out. We use the exact same area as we had used before for holding just in a small edge or a small corner, and then keep it on the hot plate. We have a stopwatch with us here. At this particular stage, we would like to operate on the stopwatch by setting it at 3 minutes and then starting to operate this, and basically the idea is that this will give an alarm at the end of 3 minutes. We need a 3-minute heating time for this particular process step of 65 degrees, and then we will go to the next step, which is another 3 to 4 minutes on the 95 degrees. So this watch is now reading about 19 seconds or so. Now this is actually an alarm system. It would tell you in advance as the time is over. It will have a beeping sound from which you can actually figure out what is the exact time for which the resist is being heated. The thing about microfabrication is that you have to be very careful about the exact hole temperatures. This right here is an illustration that the time is over. So what we'll do is we'll go ahead and pull out the resists now, the resist coated wafer now. Again, the same precautions need to be followed. You need to hold the resist from a very small corner here, and then slowly put it over the surface that we want to put it. So I'm going to now transfer this resist coated wafer onto this particular surface. It is always a good idea to actually coat the heated surface, or hold the heated surface at room temperature and let it come back to the particular ambient room temperature for the film to have least possible undulations and warping is possible. We'll just cover it in case there is any dust accumulation on the surface. Another thing I want to point out is that the environment in which this coating process is carried out is a very clean environment. We plan to actually do these things typically in clean rooms where the particle contamination may be as low as about close to 1000 ppm or 100 ppm, depending on what kind of feature sizes you are using. So essentially we will hold this for some 5-6 minutes till it equilibrates back to the room temperature, and then we will actually use the second heating step of 95 degrees and put this resist back again for about 5 to 6 minutes for the full curing action to take place, after which we will do the UV exposure of the resist using the mask. So after from its location, and put it over this plate which has been set to a temperature of 95 degrees Celsius. We start on the stopwatch and set it to about 6 minutes time. So the idea is that, after 6 minutes, as we hear the second alarm, we should be able to pick this up and then again let it equilibrate back to the room temperature before the exposure process. So we are nearing the end of the time that it takes, and there is an alarm bell now again. So what we have to do is the same thing. We'll pull back the wafer from the surface here and then put it back again on the, use just a small area here to keep the wafer or hold the wafer through the tweezer, and then put it back again on its resting place, where we'll use a little bit of time for equilibrating it back to the room temperature. So we are now ready, after this temperature is close to the room temperature, to do lithography on this particular wafer.